How's everyone?
Tired.
Yeah.
It's almost over. I'm gonna say it is. We'll start.
We start on Wednesday.
No, I was gonna say.
Yeah, that's very true. So, announcement in regards to your exams. I'll have your exam keys posted here, and I would recommend looking over those, especially when you get your exam back. Look over those and compare your exam to the key to see maybe what you missed and why you missed it. I think that's probably the best way to learn from what you messed up on. And then, of course, if you have questions about what you missed and you're not sure, then please ask me or email me or whatever. But the exam key's there. And then as we finish our exams, I'll post the blank exams. So that way you can go back to them and maybe like test yourself or keep reviewing old material, because our final will be partially cumulative. Okay. So a lot of people towards the final just like to print off the exams and work those just to see where they're at. So they'll be there as well. I'm still grading. I won't have your grades until sometime this weekend. I have another class that I'm grading as well, so it's slow when exam days coincide. But look for, I'll post an announcement on D2L when I post your grades. Does anyone have any questions on the exam or?
Everything okay so far?
Yeah, so far pretty good. There was one problem that I thought was, I don't remember exactly what it was. I thought would have been pretty easy. So the limit as x approaches 2 on e to the 2 pi. This is e to the 2 pi is a constant. It's true there is no x to plug in for, but it's no different than asking you to compute the limit as x approaches 0 on 4 or something, right? We're just looking at a horizontal line. So the limit is always that y value. So, yeah, and as I grade more, I'll know more of where like the common misunderstandings were, and I can mention that Tuesday of next week, just to kind of clear some misconceptions up. But overall, they look pretty good. Yeah. So we're going to start chapter 3. I'll post this overview if you're curious, but this just is a broad view of what chapter 3 is. We're going to start looking at derivatives in chapter 3, and we don't go in the order that the textbook goes into. Specifically here towards the end, I kind of rearranged where all the applications are last. We get all of the derivative rules first. But the derivatives in chapter 3 will continue in chapter 4. So chapter 3 is what is a derivative, how do we find it, and chapter 4 is what can we do with a derivative. So the bulk of Calc 2, or Calc 1 rather, is about derivatives. So we'll introduce the derivatives, we'll work with them, look at how to graph a derivative, and then in 3.3 and some of the subsequent sections, we get really a shortcut method to compute derivatives. So they're like derivative rules. We'll see the definition early on in chapter 3, and it's sort of tedious to work with the definition of a derivative. So then in 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.9, and 3.10, we look at shortcuts to take a derivative. 3.6 is we revisit looking at derivatives as rates of change. So like average rate of change versus instantaneous rate of change, that kind of stuff. And in 3.11, we look at related rates. Like when we relate, like this thing is traveling at west at 200 miles per hour and this thing's traveling north at 200 miles per hour. Like how fast is the distance between them increasing? So we relate rates to one another in 3.11. And so yeah, that's an overview of chapter 3. If you want to get a bigger picture of what we're doing in chapter 3, that'll be up for you. Okay, so in 3.1 we introduced the derivative. And we look at how do we calculate the derivative at a point. So the derivative, for now, moving forward too, we're going to think of the derivative in two ways. It's the slope of a tangent line, which remember is a line that touches the graph or the function in one spot. Or we can interpret that physically as an instantaneous rate of change. So in this, in this graph here, this quadratic, we can see that if I compute the tangent or the slope of the tangent line at varying points on that function, those slopes will be different throughout the curve. And so we'll talk about how do we actually find the equation of the red line, the tangent line. But the idea is based on the fact that if no matter how curvy a graph looks, if you get in close enough to it, it will always look, like a line. And so that's another, I guess, characterization of the tangent line. It measures how steep the function is at a particular point. Okay. So how we find the slope of that tangent line is directly related to how we found it in 2.1. The question on the first exam was related to this as well. Is we first look at the slope of the secant line, which again, remember, was an average rate of change. Just a slope between 2 points, A and X. And then we said if we looked at X getting closer and closer to A over smaller and smaller intervals, then the slope of a line that cuts through a curve becomes this line that touches the curve. So that process was when we introduced the limit as X approaches A, X got closer and closer to A. Over smaller and smaller intervals, we were able to determine, the average rate of change turns into the instantaneous rate of change. And that's what the first problem on the exam was. We looked at the position, and then we calculated the average velocity over smaller and smaller intervals, and then said, based on those numbers, what does it look like the instantaneous velocity is approaching? Which a lot of people missed that question. You had the numbers right from the table, but the question was asking for the instantaneous velocity at t equals to 1, and a lot of people just computed the value of s of 1, and they said that that was like 57.17, I believe. So if you were answering the question, what's the instantaneous velocity at t equal to 1, and you said this, it's incorrect because s of 1 is just the position at t equals to 1. So this would be like 57 meters or whatever the units were, right? The instantaneous velocity, it would have been something like, was it 54.34 or 56.34? So you had to look at what the average rates of change were getting closer and closer to for that problem. But that's exactly specified here with that limit operation. So then we have our instantaneous rate of change or the slope of the tangent line. So those are the same thing. And in this section, we're focusing on this equation here. So how do we find the slope of a tangent line at a given point? We have to compute the limit of this specific function here. Okay. So once we compute this limit, this is gonna output some number. And that number is the slope of the tangent line. And then once we have that number, then we just plug this back into our point slope formula for a line with that particular number here as the slope of that line. And then that will give us the equation of that line. Okay. So any questions or comments on this? We'll look at examples, of course, but this is what we'll be doing in 3.1. All right then. So find the slope of the tangent line to the graph of x squared minus 5 at the point 3, 4, and then write the equation of the tangent line. So the first thing you need is the slope of the tangent line. And the slope of the tangent line is the limit as x approaches what? So if you look back at that definition, it's the limit as x approaches a. A has to be a certain x value. Our x value that we're approaching is this here. This is our a. So the limit as x approaches 3. On this quotient, and remember this quotient is just the average rate of change, or the slope of the line. So limit as x approaches a, this piece here was f of x, so we have our given function, minus f of a, which is given as 4. So that's the point a, f of a. F of x minus a all over x minus a. So is everyone all right with what we've done there? It's absolutely crucial that we put these things in their proper place so we can compute the slope of the tangent line.
Where are you getting the x on the denominator from? Why are you putting it as just x minus 3?
Because it's just the change from a to x is just the difference between x and a. So it's just there in the formula.
Okay.
Because remember, if we compute a slope, when we say like it's the change in y over the change in x, we just have to make sure that these two match. That this input here is this number here, and that this input here is this number here. Yeah.
So then why wouldn't the denominator be x squared minus 5 instead of x?
So the denominator is just x because it's not x squared minus 5 because the function is x squared minus 5. So the function itself is up here, the x is down here. Any other questions? And you know, like to tie this in to chapter 2. In chapter 2, we spent a lot of time looking at all different kinds of limits. Here in chapter 3, note that this is to define the slope of the tangent line. It is a very specific limit. You have to take the function minus the y value, divide by x minus the x value. So every limit doesn't give you the slope of the tangent line, right? Like if I compute the limit as x approaches 0 on sine, and that outputs 0, that is not the slope of the tangent line. That's just saying that as x approaches 0 on the function sine, what do the y values approach? So not every limit is a derivative, but the derivative or the slope of the tangent line is a limit. So yeah, let's annotate this here. There's our f of x minus a over x minus a. And that's the limit as x approaches a.
The top one's f of a.
Yeah, f of a, thank you. So notice, just by definition, the slope of the tangent line in terms of the limit, it looks like it's undefined, right? Because as x approaches a, the denominator is 0. So that's why it said in the definition that if this limit exists, that is the slope of your tangent line. So not all of these limits will exist, but I think as we start to do these computations for the slope of the tangent line, that you'll start to recognize familiar patterns, you know, with square roots or with complex fractions, those kinds of things. All right, so let's just simplify this. top is just x squared minus 9, and the bottom is x minus 3. So can we simplify that? I mean, we can't evaluate the limit directly as it is, but yeah, so we factor, divide out terms, right? So what does that simplify to? It simplifies to just x plus 3. And then we can compute that limit. As x approaches 3, x plus 3 approaches 6. So 6 is the slope of the tangent line. It's how steep x squared minus 5 is at the x value of 3. Does anyone have any questions about that?
Are we gonna figure out how we can write the equation of the tangent line? Is it just 6?
No, so that's the slope of the tangent line.
So that's m.
Yeah.
And then we can figure out.
Yeah. So that's the first step, find the slope of the tangent line. The second step is just to plug all of that information back into the equation of a line formula. So I'm gonna just abbreviate equation of the tangent line. So it's y minus y1, or y minus the y coordinate of the point, y minus 4, equals to the slope of our tangent line here. The slope of our tangent line times the quantity x minus the x coordinate. Okay, so we have 6x minus 18 plus 4. As the equation of the tangent line. So, are there any questions about this example?
On an exam, would those answers be correct? Or do you want us to put it in the form of y equals?
Yeah, so the instructions might say write the equation of the tangent line in slope-intercept form, or write the equation of the tangent line as y equals.
Okay.
So we just verified what we're doing. So there's our quadratic x squared minus 5 at the point 3, 4. We wanted to know what's the slope of the line that touches the function at that point, or how steep is the function at that point. So there's our tangent line at the point 3, 4. And so we'll notice that it only does touch at that one point. We just have to get closer to that curve to see that there is space between until we get to that point, wherever it was. So it is only touching at that point. No questions on that? We do spend a whole lot of time in chapter 3 just talking about sort of the mathematics of it, right? How to compute how to find certain things. But really the applications to the slope of a tangent line are endless. Because if you think about the slope of the tangent line as measuring the instantaneous rate of change, that rate of change could be any quantity you measure, whether that's time, whether it's altitude, whether it's population, whatever the case may be. And in any situation where you have a particular model and you want to know, okay, at this very instant, time equals to 1.357, how fast was the population increasing or decreasing, then that's when you would use a derivative or slope of a tangent line kind of thing. So the applications are really extensive. We don't really have a lot of time to go through those because it's all how do we find derivatives for particular types of functions, but you know, it's very in depth as far as applications. Okay. All right. Similar example, find the slope of the tangent line at -1,4 on the function 4 over x squared, and then write the equation of the tangent line. So we have the slope of the tangent line will be the limit as x approaches what? -1 on what? What are we looking at here for our quotient?
4 over x squared minus 4 over x plus 1.
Okay, so there's our function minus the y value. And then we divide that by x minus the x value.
X plus 1.
Again, the denominator is 0, but hopefully we recognize that as a situation where we know what to do, how to simplify that quotient. So what do we need to do here?
Squared. Is that one of
Um,
the ones where you plug in and do all that stuff?
You said 4 minus 4x squared over x plus 1.
yeah, and so the way we approach complex fractions is we look for the lowest common denominator. The lowest common denominator is just x squared, and then we're going to multiply the numerator and the denominator by x squared.
That's what I was trying. I don't know the wording, squared.
Just to clear that, just to clear the smaller fractions. All right, so what we have is 4 minus 4x squared. And remember with these, we wanted to leave the denominator as it is because that factor of x plus 1 is causing us the issue for computing this limit. So that's an improvement, right? We don't have like fractions within fractions anymore. We just have a single numerator and single denominator. But we're still as yet able to compute that limit, right? We're still dividing through by 0. So the hope here is that we can factor the numerator and we can cancel something with that factor of x plus 1 on the bottom. So we'll just factor out a 4. When we factor out a 4 from the top, then we have the difference of squares, right? It's 4 times 1 minus x squared. So we factor out the 4, then factor the difference of squares. We still have this on the bottom. All right, so then we end up with 4 times the quantity 1 minus x all over x squared. So the issue with the factor of x plus 1 has been simplified out. Now we can compute the limit as x approaches -1. What's the limit as x approaches -1?
8.
Yeah, so we'll just plug that in here. This is 4 times 1 minus over the square root of -1, or sorry, square root of -1 squared. So we have 4 times 2 over 1, which is 8. So again, that 8 represents the steepness of that function at that point, or the slope of the tangent line, or if it was sort of like a physical application, 8 is the instantaneous rate of change. Does anyone have any questions on what we've done? So there's the slope of the tangent line. The equation of the tangent line is y minus the y coordinate equals to slope times x minus the x coordinate. Or y is 8x plus 12. Okay, so here's our 4 over x squared. We're trying to find the tangent line at this point. And we said it was 8x plus 12. Again, just get sort of close, just to see that it's only touching at that point. So we can see the difference between. And then here we can see this cross again, right? Well, no. Sometimes your tangent line, depending on the function, will cross it again, but that's okay. Just know that when you come up with the equation of the tangent line, it will touch at that point, guaranteed. As long as you're doing that correctly, but. Do y'all have any questions on that? All right, then try this one.
Then it gets ugly over here. Sit up. And then you can do like substitution. Yeah. 1 plus 3 is going to be 2 plus 2. You got it.
You're trying to get rid of something that makes it zero. So if you cancel that, you will immediately cancel all of the literally the rest of it. So you just, that's what I was like,
That's where I don't know if I.
okay, so those cancel out and then they you just have to by each other. That was the part that was tripping me out for some reason. I was like, you can't do that. That's not a thing that's possible.
I didn't even think about doing that.
As long as it makes sense in the end, you're right. I got nothing. 7 0 plus 7
Plus 1.
plus 1.75. Yes. Yeah.
For
Yeah, I don't know, that's why it's weird. Factor it out. Or you multiply by the reciprocal. And if you just, you know,
what's the
this
other
is multiplying
part of
on
this that
This is supposed to be so when you multiply this times this
that gets away?
it goes away, so it's just whole. And then the middle 2 cancel out. And then 2
Right, yeah.
You're so told like, oh,
I was trying to,
square. I'm like, oh, totally.
I was trying to foil this without having an extra
Or
square.
wait, why don't you do
It's
I forgot that just addition is just part of it. That's true. That's not a thing. You wouldn't have to do it plus one.
minus 4.
I was like, wait,
I got syntax error on my computer.
Oh, so then you'd be left with -1 and then that would cancel. Oh.
And then it gets a little prettier.
It gets a little prettier and you just make sure you
And then
have
at the end, it gets ugly again.
+2. It's not really that. Because then you wind up getting one.
I don't know, like, the formula for the line is 1/4x plus 7.
I know that's a little kind of weird. So it's just like,
Okay, and then the
like
slope
a
is
shallow slope. It's just like.
I don't think I'm even thinking right.
Yeah, so that's what I got.
And what, I just like forgot how math is, apparently.
Happens to be like two.
Because literally I saw x plus 3 minus 4 and I was like, gotta foil it. Addition is not applicable.
We haven't done addition in so long.
Yes.
After a lot of thinking,
Yeah.
yes.
Well, it's good, right?
We literally did 4 hours of labs. Yeah, we did 2 hours.
Okay, in that 4 hours, did you have this one thing at the side of your nose?
No,
Wait,
but
these things
Of
change
time.
colors
the
though.
things changed colors and it was really cool. And it changed to like a dark blue and then changed back to the original color.
It was so pretty.
But to be fair, it was finishing up one lab and then completely doing another.
Yeah.
And then we left it a little
Yeah, so
early.
technically this
Like
is.
3 hours.
Like physical geography for one of my science credits. It's basically art class. I get to doodle on maps.
That's awesome.
I highly recommend that.
We've all got different.
Chem 101, been there, almost failed that. Chem 111, been there, almost failed that.
You wouldn't square it.
Chem 112,
If you square it,
actually one on the first
if you
test.
square, you have a totally different function. That's like me giving you A and you saying, I want to work with A squared instead. So it's like, yeah, right. So
Do you use the conjugate?
yeah.
That's just so much easier.
Yeah.
And it worked out really smooth. So, yeah.
Cheryl saw me a lot.
Cheryl and her greedy.
Yeah, it was literally I was in her office maybe when she was having her.
I did?
Yeah, I still.
I showed up late. I didn't know That's awesome. Okay, so you want to
So how is timing 1 by 1 4?
Okay, remember the conjugate, so it's the first term plus the second term.
What about what I just
Because you have what, you have A minus B.
I was trying to help.
I distributed it in.
So we leave these two things alone, we just change the sign to
Oh, you
get the conjugate. So that's the conjugate.
Yeah, just like pull out the negative
I was like, what are you doing?
I was trying to keep the conversation about how bad I am at chemistry. Yeah, but we took biology together. That's pretty fire. Not like the most fun. Like, it's just like,
It was fun. I like bio.
Yeah. I like the sound.
Yeah.
love bio.
Bio is the best.
It's like, that was cool.
This.
By the way, about chemistry, because I have a really hard time with chemistry. Because like I can't.
There's a reaction. You watch
Yeah,
something.
you like write this equation that describes the chemical reaction and then start the reaction and you're like, oh, those are 2 completely separate things. In my head, like, those
It went from
don't,
pink to purple.
like great, like love that for me.
Don't know what it is, but it changed color.
Yeah, no, after that.
And then I had to find the and then how it breaks.
Yeah, and then
So I ended up very specifically. Alright, this makes sense. Where did the extra shit in the middle go? That's the question.
yeah,
It's like, okay, there's a little bit of energy. Why is it negative?
yeah.
I do that with Forrest.
Which chemistry are you in? Oh yeah, it's just like. So if you ever need help in 111, you can ask her, not me. I'm not gonna take That's me with this class.
Yeah, I was able to get rid of this.
But I took this class a year and a half ago. So it's just like learning it all over again. Like, I don't know how to tell you, I've always been good at it. I got a B in pre-calc, this is basically easier.
That is one thing that I counted myself lucky. I've never been good at this, so I try hard.
See, I was like a genius in high school, and then I was like, you know what, junior year, I'm gonna just take those classes because I was the smartest.
There were answers I knew.
And then I took college algebra. Yeah, right. And then I took college algebra, and I'm like, I was a four-credit student, right?
I knew that.
College algebra to C. And then I was like, okay, well that hurt. And then I took pre-calc, and I was like, B. And then I was like, Mom was coming back. And then I took
Okay, so
calculus.
1/4, most of y'all had that. Anybody that didn't get that, have any questions or need something explained? Remember the radicals involved, when we see those, that's, you know, the bulk of the time is implementing the conjugate of the radical portion, so we can get rid of that. Okay, so then the equation of the tangent line. What was it? Oops. Y minus 2 equals to times x
Minus 1.
minus 1. Okay.
Reach my level. Because my plate's pretty. Because it's like make sure my company was rock solid after those.
Okay, I'll come right back to that.
Doing calculus. You need your picture too. Social Security Administration. I had some call up over.
Okay, so that's what we're looking at. There's our function, there's the point, and there's our tangent line. I don't think I have one. Just- All right, sorry, if you're still copying, I'll post these, so don't worry too much about that. We have to move it along. So the formula we were dealing with was kind of this situation here, where we had some function, we had an x value, we had an x value again, which was a, and then we said, well, let's first compute the slope of the secant line through that, through those 2 points. And then all we did was put a limit on the secant line, which causes this line to eventually, as x is approaching a, what we're looking at is that this secant line becomes this tangent line right here. So we just have this line here instead. So there's another way to describe what's happening here in this setting, and this alternate formula, I think, is way more conducive to computing a derivative when we start computing derivatives by their definition. So we'll still call this, well, what do they call it? They call it A and A plus H. So instead of calling one X and the other one A, we're going to call one A and then the other one A plus H. And remember that A plus H just indicates, that H just indicates the distance from A, right? It's how far away from A we are. So we can describe a location by something, A, and then any other subsequent location on the same line as just the distance from that starting point, if you will. So that's all that is, A to A plus H. Still have this function, f of x, but then we look at f of A and f of A plus H. Construct the slope of the secant line in the same way. Just the slope between those 2 points. So we have the y value, y1 minus y2 all over x1 minus x2. And then, of course, here on the bottom, the positive A and the negative A are gone. So the change in Y up top, the change in X from A to A plus H is just H. And so that's our different formulation of the same thing that we've been doing. So we have an alternate definition for the slope of the tangent line, which is just given as the limit as h approaches 0. So if we go back to that, we were making x closer to a, computing that. Here we're making h closer to 0. So as h approaches 0, this x value approaches this x value. So that's our alternative definition. Still gives us the same thing. It's still outputting a number, which is the slope of the tangent line. So what we're given is still the same. We're given a point and we're given a function. If we're computing this equation of our tangent line, then we need to compute this, or we need to find this. Before we compute the limit. So everything else would be given. We find what f of a plus h is, and then we work through the limit. So you should recognize that maybe vaguely as that looks very similar to difference quotient that you compute in like a pre-calculus class or an algebra class. So just to see that, we'll go back to our example we had earlier, x squared minus 5 at the point 34, and we'll use this alternative definition to compute the slope of the tangent line. So it says that the slope of the tangent line would be the limit as h approaches 0. And we have to find the f of a plus h. What is our a here?
3.
It's 3, right? So we have to find f of 3 plus h minus f of 3, which is just that y coordinate 4, all over h. So here, off to the side, let's find f of 3 plus h. What is f of 3 plus h?
Zero.
Do what?
3.
There. No, a is 3. f of a is 4, or a plus h, f of a plus h is 4. What would f of w be? W squared minus 5, right? So what's f of 3 plus h?
3 plus h quantity squared minus 5.
It's 3 plus h squared minus 5. So let's just figure out what that is. I have 9 plus h squared plus 6h minus 5. Yeah, so that's just h squared plus 6h plus 4. So we just put that in. By the definition, as h goes to 0, you're not going to be able to compute that limit directly. So in this setting, instead of looking for the factor in the previous definition, the factor of x minus a to cancel out, here we're just looking for a factor of h to cancel out from the top and the bottom. Yeah, so the 4's go away on top, and then we have a common factor of h that we can pull out. So combined line terms factor, and the h's now divide away. Limit as h approaches 0 on h plus 6 just gives us 6. Which, if we go back to that first example, that's what we had as the slope using the other formula. Anyone have any questions on that? Yeah.
So I did it a completely different way, but I came up with the same answer, and I wanted to make sure it's not a mistake.
Okay.
So basically what I did was, I'm used to doing the x plus h squared minus 5,
Okay.
and then you subtract x squared minus 5 and you divide all of it by h.
Okay.
And then once you get down, you can plug in 0 for all the h's, and I was left with 2x.
Okay.
And I plug in x, and I get 6.
Okay, that's fine.
Okay, cool.
Yeah, because we're doing there, or what you're doing there, is what we do in 3.2.
Okay.
When we talk about the derivative as a function, as opposed to just
I
finding
was
the
getting
derivative
really
at a point. Yeah.
Great.
So yeah, the idea in 3.1 is to how do we calculate the derivative or the slope of the tangent line at a point? And the idea in 3.2 is how do we calculate the derivative as a function so that all we have to do is plug the x values in. So no matter what point I give you on a function, you can plug that x coordinate into another function that will output 6, as opposed to having to compute this limit over and over and over again for every single point you have to find the derivative at. We can get a function in return as opposed to a number. And we'll see that in 3.2. I think it'll make more sense when we see it. Okay. All right then, so why don't you all try this example using that alternative formula.
What's the point of that alternative formula? I mean, I guess in the sense of when would you use that versus the way that we just did in the beginning of the chapter there?
Yeah. So the difference between the two formulas is there really is none. I think for computing the derivative, it's more conducive to look at the second formula that we did with the a plus h than it is for the first one. But either of the two will just output the slope of a tangent line.
You typically use the second one when it has h incorporated in it, right?
Yeah.
Then you could just find h just just by looking at the x-axis though, wouldn't you? Because it's just the difference
Yeah.
between, x final and x initial.
Yeah, but we don't want to specify a particular h, because x initial is 0 and x final is 1. So from that x location to that x location, that h is 1.
Right.
But if then we're like right on top of it. We want to look at as we get closer and closer to it. So
we're using it as a, or I guess solving it, however you want to look at it, as a limit, not as
Right.
not as the equivalency of x at a single function.
Yeah,
Or at a
exactly.
single x value defined function.
Yes.
Kind of limit.
It's almost like our variable in this limit now.
Okay.
Yeah.
Is h always equals 0 when you're using it like this?
Yeah. So in this formulation, h is always getting smaller and smaller. H approaches 0.
That's what it did. Because I didn't have the
Do what? Sorry. No, engineer people draw lines through zeros. Math people don't do that because lines through zeros mean something completely different. That means an empty set. So that's why math people don't do that, because it has a completely different meaning. Yeah, it's fine. We all know, like, we're not in like a set theory class, so it's totally fine. Yeah. I guess I can make my zeros more elongated, but by this point it's muscle memory, so I have to like force myself.
What?
Right on this side. Oh, because, no, don't worry about it, okay?
Yeah, you're on the.
Yeah, I was comparing notes to figure out what I needed to do on this side.
That is not correct.
You can't just say that. Wait, which one was this not correct?
No, it is me, sorry.
Okay. Who's to say?
Sorry, I started myself.
Wait, I don't get why you guys are so confused. Hold on, I need to get there.
Yeah, that's fine. I think at this point though, I would plug my.
Just the answer.
So once you get to this point, get rid of all that, do the limitation of this. Yeah, but I would plug the 8 in. Because your limit is operating, it should be. And so, really the only variable I would want to see in there.
That's how I think the
Yeah.
Just all over each.
Yes. And then after
I'm actually.
you should have 2 variables.
You have to put that into that and subtract it by the size. Oh, no, you're right.
I don't know if they cancel or not.
No, I don't think.
The point you're giving here is A comma and then point A and then after that, then U should be 0, right? Yeah, you have to simplify it first.
I feel like that's like fine. And everything will.
So what I would do is start off by immediately.
I mean, like, I'm not confused yet. Maybe I'm just not as far as they
And that way I just end up with something in terms of each, something that involves A.
This. That. I feel like this isn't a good one to use. I agree. I'm trying to figure out how to do it. Mike's got something. Mike thinks he's got something.
He's like, I have to figure myself
I got one. That's funny.
Yeah, because now it's like the last time.
Well, you
I think I'm doing this wrong.
Yeah, so the point of your emails ID though is to clear
Oh, wait.
This one was let's see.
Oh, okay. This is
That
why does it?
not one. Yeah, no, that's right. Because the we need not one and not one. You just do it, so yeah.
Oh, I see. You're
Okay, right now I have negative 1 over 8.
and you're doing that to scale.
All of this is what you would do.
That's what it's now. I'm like, where do I go? It's a well, this whole, no, it's this whole function is mom equals bechehet. So
Oh, that's why I have this. Oh, why did I not take that out?
So this is right. But then you end up with dividing by 0 again.
Much more helpful. Because then,
No, you can't pull out one of those and that ain't no. So it should just be one.
and then,
Right? Or am I just screwed? Or should it
The only thing is that
I want to
Yeah,
go with
because it's not each square.
because I want to force each other to just denominator. That,
Which makes it 2.
that's still
zero. Fraction, you go from there to there. This is after multiplying. Essentially, you get 2 minus 1 plus 1. The age you're left with. I got negative 2. That's how I did
I'm gonna try it. I honestly have no idea.
I think we have basically the same rules. I think one of us has the
Right, but you gotta remember is that even before you do this, the 0 minus 1 makes it negative. Like you have negative,
Like, I think I figured it out.
you gotta keep in mind if you're.
This negative has to distribute,
So
so
that negative has to
minus
distribute there. So it's
minus
1 minus 2h minus 1.
I don't know
Which
what
gets
that
you
means.
negative 2h minus 2. No, 1 minus 1. Yeah, but only if you don't distribute that negative
If I understood what you said.
which is
And
what I
that has to
have.
be negative.
It's which case you did it. You did it out.
So that's.
Do I have
So if you write that out to be 1, minus 2h minus 1.
Yeah, but that gives you 1.
Start back from
Same thing as 1 plus negative 2h plus I think we both have the same thing. We just have the wrong side.
I think we agree on 2.
Yes.
One question.
If we're not intending the other methods of like it's a direct substitution.
I'm redoing
You're just plugging numbers in what they are. So you find x equals that exact number.
I need to start remembering the season because it jacked me up.
So like in those first examples, alright, so like in these ones,
That's not an answer.
That's just what I'm saying, but I know it's.
That is correct? Okay. What the heck?
Now, how'd you do that?
and then on these.
I have mine written really weird. You probably don't want to read mine. I have the order of it really weird.
Okay.
Limit is also
Yeah.
different.
It's like serpentine.
You're focusing on the chain,
And I'm gonna sign 2.
not the chain
Alright, so that's the right place to start.
Okay.
Why do you have a minus 1 on this?
Right.
Am I just wrong to put a plus 1?
Well, because you have to distribute the minus. Because of this, you have this written down. This is supposed to be a minus 1 right here.
So that,
And so
Oh, yeah.
when you plug this into there, you have to distribute the negative.
Oh, okay.
Will you, how is this looking so far?
I wouldn't multiply these. I'd keep them separate.
yeah,
Just to
keep
make it-
your denominator
Okay.
separate.
Yeah, just that way it's easier to cancel stuff out. Oh, so this is multiplied to that.
So just a word of advice, when you're using this definition, plug in the A first. Don't keep the A and the H floating around. Okay, so once again, we have these fractions within fractions, multiplying through by the lowest common denominator. Don't forget to distribute this 2h plus 1 to both of these. That first one just gives us 1. I don't know how to write that here. This is 1. We have a minus 1 times that quantity, so that's a minus 2h and a minus 1. Don't forget to distribute that negative in. Okay, so then that just simplifies
Yeah.
to negative 2h over h times 2h plus 1.
Cool.
The h's now cancel out.
I got rid of the first term altogether instead of putting a 1 in there, so then my 1's gonna be cancelled.
As h goes to 0, 2h goes to 0, so you have negative 2 over 1, which is negative 2.
Yeah, I did have a sign.
That's the slope of the change down.
We got it. We got it.
It's a long road.
It's a good thing that was on the test.
That was a long one.
Yeah.
That was rough.
Yeah, that was real rough.
So that's one that you would not use H with, you would just go with.
Yeah, why did you, why did
To show that you can do whatever you put your mind to.
And then we have to put it in the y minus 1 equals negative 2. 1 equals
Thanks for letting me see your notes.
they're only mine now.
and that's 0.
I made this a lot.
And it like hurts. Like it really hurts right here, and then it like, it stops hurting right here.
Trying to see
I can't. I have to wear a glove anyways. Because I mean, I feel like this is one of those rules that you're like, probably is kind of obvious.
Yeah, it's the same thing, but it's, if we're distributing this to this, you have this negative 1. You have that negative 1 from there times this right here. Because we're multiplying it in here and here. So that's where the negative 2h minus 1 comes from.
Because I was commenting on the fact that it hurts. That red stops.
Yeah.
I say go to the doctor as a
All right, I think we should take a break. Anybody have any questions on this? You're confused? Okay, so this
See, I only play on Xbox.
And PlayStation.
Oh, okay. Yes. As all PC gamers think they are. And as all PS4 gamers think they are.
We know.
I have one that my brother made an Xbox.
I'm pretty sure that
Because he's saying.
All I have is a MacBook that doesn't have anything powerful enough to play. I thought about getting that when I was looking to buy a laptop. I thought that was like a pretty expensive gaming laptop, but
What I like to do is, I like to game for 5 years in advance, so that all the games are super cheap, and the new cards are like $40 a piece. So I'm just like, sweet, I can overclock this machine, I'm out $100 total. I can play games from 5 years ago at really high fidelity for the time, enjoy the crap out of them. I'm never out $60 on a charge.
Yeah.
So you actually want to get rid of that. One of my friends got it. That's what's causing me to be able to apparently they had a roadmap.
is the one.
it has to wait.
All of them?
No, just one and one.
I got you.
might make it. Like, I couldn't.
Got it on sale on Steam.
I was just trying to.
$60, but I
For the last couple of months, I've been
Does it pop up when your heart rate rises?
I think so.
Warhammer.
Have you ever got the thing with like your heart rate reaches 140?
I understand. Like, my reflexes are
It'll
now
like
old
beep
man
you like
reflexes.
say like my heart rate has gone up.
I'm just like, no, I wanted to get there and I showed
It's taking 10.
my daughter.
My heart-
9 years old.
Right?
Like my breast.
All right, y'all ready?
The only way I know is to
Y'all ready to party? Okay, so 3.2 has us dealing with the derivative as a function. So we looked at the derivative in 3.1 as just this sort of singular thing existing at a point. And it's kind of, here's the idea. That's what we computed in 3.1. What was the slope of this red line at that particular location? But as we move across the various x values of that function, we see that the slope is different every time. And not every time for every function, but in general. So that's kind of what we're after now. Here's a specific example. The slope when x is 2 is 32. Then it's at 2.9, it's 3.2, and so forth. We can see as the x values change, the slope of the tangent line changes as well. So what we're after is, instead of coming out with just the slope of a tangent line at a point, and then having to recalculate that at every single point, is there a faster way, or, as we'll discuss, is there a function that will give us the slope of the tangent line at every point? Okay. So that's where the derivative, the definition of the derivative here comes in. And so this is the derivative provided the limit exists. A term that does show up frequently is this term that's in bold here. When we say that f is differentiable, we just mean that the limit exists, or that we can compute the derivative at a particular point. That's what it means when we say it's differentiable. The derivative exists at x. Okay. So to contrast this one with the one from, I'll just write this one out. From 3.1, we had the limit as h approaches 0 on this thing. And this output some number that we call the slope of the tangent line. So notice the only difference in the definition for the derivative at a point from 3.1 as opposed to the derivative at all points x is it's f of x plus h minus f of x. So when you see those a's here, it can be confusing because of the notation. We've got h's, we've got x's, we've got a's. Just the a is just some fixed x value, like 5 or negative 12 or 4. X is just something that could be wherever. It's our variable. So when we look at modifying the definition, instead of saying let's compute it at a and a plus h, that we'll just consider x and x plus h. That could be anywhere as opposed to some specific location. What we get from this definition here, as we see with the notation, is we get a function in return. So no longer outputting a single number, but it's going to output some function of x that's derived from the original function that we call the derivative function, f prime of x. So the prime is there just to indicate that it's related to f in a specific way. It's derived from the original function. It's the derivative function that gives us the slope of the tangent line at all points on a particular function. So as we move forward, you'll start to see examples where it says find the derivative, and we'll talk about shortcuts. The shortcuts are basically a way to bypass computing this limit every time we want to find a derivative. However, if the problem says that you need to find the derivative using the definition, then you have to use the definition here. That's the definition of the derivative. So this is one of the main pillars of calculus. This is a very crucial and important definition. So since we're already acclimated or a little bit used to computing the a plus h thing from 3.1, then we'll just jump into computing the derivative via its definition for the function x squared minus 5 again. So just go back to this definition. Worth pointing out here, excuse me, it's worth pointing out that we're given the function, we're given f of x, and it says find the derivative on for f of x. So really all we need to do outside of computing this limit, we still need to find this f of x plus h. So we find that's almost like a side computation. What is f of x plus h? And then we'll plug all of that stuff in here, subtract off the function, and then hopefully compute the limit. So find the derivative. Let's first find f of x plus h. So we have f of x plus h is the quantity x plus h squared minus 5. And again, that's x squared plus h squared plus 2xh minus 5. So all of that goes into our definition for f prime, which is the limit as h approaches 0 f of x plus h minus the function f of x. So here, just be careful, we're subtracting off the entire function f of x. So subtract off the entire thing, not just a part of it. And all of that's over h. So this definition that you explicitly see the difference quotient. If you remember the difference quotient, the definition of the derivative has the difference quotient in it explicitly. F of x plus h minus f of x over h. So then we'll simplify this limit. By the definition, the reason we're not able to compute this directly is because, again, the denominator is approaching 0. So we've got to hope that there's an h up top that cancels with that h on the bottom in order to compute this limit most of the time. Okay, so we have our x squared minus our x squared. We have the negative 5 minus the negative 5, so those are gone. We're just left with h squared plus 2xh on top, all over h on the bottom. Do what?
refactor on the YouTube.
Yep, that's what we'll do. And notice this just says find the derivative. It has yet to say find the slope of the tangent line at a given point. So all we're looking for is the derivative function, and then we'll go from there. So right, both of these terms have an h in common, so we're going to factor the h out of the top. And divide with the h on the bottom. So we just have h plus 2x left over after we do that.
What does finding the derivative allow us to do?
It allows you to find the slope of the tangent line at every point on x squared minus 5. So notice what happens here as h goes to 0. What we get is, like we said, a function. And that function represents the slope of the tangent line at all points on the original function. So f, we'll just write this out in a condensed version. This f prime of x is 2x. So this is the derivative of f of x we'll write that out, what we just said. This function will give us the slope of the tangent line at any point on f of x. In other words, that's the instantaneous rate of change, that function f prime, that's the instantaneous rate of change all along the function x squared minus 5. So if we look at the question, well, what's the slope of the tangent line on x squared minus 5 at the point 3, 4, like we computed in 3, 1? We had a separate limit problem to compute that particular thing. Then we could ask, well, what's the slope of the tangent line at the point negative 5, 20? Then you would have a different limit from 3, 1 computing that. Negative 2, negative 1, different limit computing that, right? So from 3, 1's perspective, each one of these questions about the slope at a different point requires a different limit setup. Whereas here, we've come up with a function that will describe the slope of the tangent line at all points on x squared minus 5. So then the question is, well, what's the slope at the point 3, 4? Then we're just going to take our derivative function and plug in that x coordinate. So that's, we computed that 2 different times, and we got 6 both times. What's the slope of the tangent line on x squared minus 5 at the point negative 5, 20? Well, we'll just take our derivative and plug in the x coordinate here now of negative 5. And at negative 2, negative 1, evaluate f prime at negative 2. Okay. It's a much more efficient way to compute derivatives at certain points. Anybody have any questions on that? No? Okay then. So find the derivative f prime of x for function 1 over x squared. I'll give you, let's take 7 minutes to do that. That way it'll be 250.
I'm not there yet. Give me a second, and then we'll talk.
Place, so I guess this proves that.
Yep, that's where we're at.
That's all I'm left with.
Do you divide or multiply with that? You do that?
Because you have to do this, because you have to get the lowest common
Yeah, so one.
denominator. So literally cannot. So you have to multiply that by x squared, then multiply that by x squared, and then you have to multiply the top by this, and then the bottom by that, so that the numbers are denominator.
Okay, multiplied by x plus
Yeah, no, it's not gonna be great.
Oh, that's just.
Okay.
Square, so one square.
Okay, so that changes it.
Minus the original.
Zero, so I would do.
Yeah, you know what I mean? So then you have a one over x squared plus h squared. Let's just.
If you can,
Rid of that.
you, my friend, are correct. Yes, it should be. It's 1 over squared. So,
Yes, because they cancel, they still cancel out. Yes. So it's h squared.
And the bottom is h times x squared plus h plus x plus h
Yes.
squared.
Yes,
That's where, that all happened, and then I just like, okay, there's way too many variables now.
H x plus h. Okay.
Wait, wouldn't this just be 3x?
Wait.
Or x cubed?
Oh, wait a second.
Okay. I can put an h in.
That's why. Oh, I got it. I got it
So
now.
that goes away. So this is
Because if you do the same thing, it's just 1 over 1.
No. Because you'll have this on the bottom.
Yeah, so that, if I multiply this all over, this cancels out.
So,
We just have a 1.
Why would you multiply?
Oh, so what you're saying is I'd have this right on both.
That's the
Because if you're multiplying through by the denominator.
minus side.
Yeah.
I have negative 2.
You're saying that this one.
Where did you go?
where did you go?
It's kind of like a cross multiplication. One thing is I think. That makes sense. If I had this
But you can do it all
like
over.
that, and I'm gonna multiply it by this times x squared.
Wait.
This thing over here, all of this is gonna cancel here. So you're showing to be left with the x squared on this side. Because that's going. This thing here, the x squares go away, and you're left with just that minus this quantity. That makes sense?
I think. Maybe I'm checking it.
Alright, so if I have this complex fraction, it should be yeah, don't say that. It should be one, right?
Yeah, that's nice to see right now. Let's break it.
Are we at the same point?
Yeah. Oh, yeah. It's just like behind the space. I just put 0 in. 0 here.
Yes.
Right?
Yeah.
I saw that as a Y. I'm like, how did you even get a Y in there? What are you doing? Yeah, I was giving you.
So it's, yeah.
Should we take the,
Over.
can we take h out of grade and x out of grade?
Which is 2 minus 1.
No, I mean just for the if you do a little shortcut way to get going.
Would that be right? But flip it off.
Let's try it. 2x.
Okay, I'm taking h out of the top.
But we couldn't, I'm not sure if it'll help.
Well, let's see what
Because I don't
maybe
think,
we can cancel something out. You're taking x to the
Now take it 10 minutes.
I don't know if it helps us at all.
Because it's a power of one or is it a power of ten?
Minus 2.
Oh, it's.
So I just want to, I haven't made it around yet all the way, but there is really, in this instance, with fractions within fractions, the strategy is always to get rid of the smaller fractions, right? By multiplying through by the lowest common denominator. I think it's a much easier situation to deal with if you just leave the x plus h squared. Either way, it's going to come out to be the same thing. It's just that we'll end up squaring it later. So I think a lot of times finding the lowest common denominator trips people up because it's like, oh, well, it's common to both of them, and the x squared would be the lowest common denominator. That is entirely not true. That's not the lowest common denominator.
It's just everything over squared times.
I wouldn't even think about lowest common denominator. I would just think about any common denominator.
X squared times x plus h.
Any common denominator is going to do what we need it to do, and that is clear the smaller fractions out of the larger fraction. So I'm just going to multiply top and bottom by x plus h squared times x squared. Just take all of their denominators, multiply them together. That's your common denominator to clear all fractions. Also need to do the bottom too. The only advantage of the lowest common denominator is it keeps you from having to simplify at the end. But the lowest common denominator is harder to find in most cases. Okay. All right, so let's see how this pans out. And I'll keep the limit here. If you want to simplify all of this and then apply the limit, I'm okay with that. Okay, so the x plus h squared, x squared, is going to be distributed to both of these terms. Let me just write this out because this one's it's a little bit more messy than other ones. So that's kind of what that looks like initially, distributing through. Yeah, and we'll have this. We're just going to leave this on the bottom. Remember, the h on the bottom is what we're trying to cancel out, so don't multiply all of that in, because then you'll end up having to factor it out anyways. So just leave that alone. All right. The x plus h quantity squared cancels here. We're just left with x squared. The x squares on the second term are gone, so we're left with a minus 1 times the quantity. And then still over this thing. So don't forget to expand. This is -1 times the quantity x plus h. So you've got to expand all of that stuff first, and then everything gets multiplied by a -1. So I might run out of room here, but let's try it. Okay, so we have our x squared. We have the -1 times the quantity x plus h squared. So that's x squared plus h squared plus 2xh. All of that needs to be negative, or sorry, multiplied through by a -1. All right, so then we have an x squared minus the x squared. We've got a minus h squared and a minus 2x on top.
2xh.
2xh, yeah. Sorry, I said that, but I didn't write it down. That's plus 2xh there. So now we'll distribute the negative 1 through and combine like terms. Okay, similar situation, both terms up top have an h that we could factor out. We'll cancel with the h on the bottom. So yeah, I mean, it's a little messy, but you know, I hope you notice at least some common themes throughout when we're working with these things. Okay, so we have h plus 2x on top. The h divided from the bottom, so x plus h squared times x squared on the bottom.
So the numerator should be negative.
Oh yeah, yeah, sorry. We distributed that negative here and here. So minus h minus 2x. Thank you. Okay, so now h goes to 0. We eliminated the issue of h in the denominator, so as h goes to 0, we have minus 2x on top. We have 0 plus h, or sorry, x plus 0 squared. So that's an x squared times the other x squared. We have minus 2x over x to the 4th, or minus 2 over x cubed. So that's our derivative function for 1 over x squared. So that's the problem, right? If I want to find derivatives of functions, imagine a function like the sine of x squared minus 1 over x squared, right? You got a whole ton of work to do. So it's really inefficient. Yeah.
Factor out the h to cancel them. Oh, never mind. I was like, do you factor out that negative 2, but you can't cancel it if it's not negative on the bottom?
Yeah.
I answered.
Right. Okay, good. Yeah. So the problem with the definition of the derivative is it's super long and tedious. So that's why we start looking at shortcut methods in the next section.
We do that.
If it says find, like, once we get all of these tools, if it says find the derivative, 99% of the time you're using the shortcut. If it says find the derivative using the definition, then yeah, you've got to go this long route. If it explicitly says to use the definition, you got to do that. Okay. Are there any questions on that? Yeah.
The step from negative h, at negative h minus 2x over x plus h squared times x squared. How do we get from that to x squared?
This one?
Yeah.
So we just applied the limit here.
Oh,
So that was 0, so that's just 1x squared, and that's another.
okay, got it.
Any other questions or comments? And what do you see here? This is, even though we're doing calculus, the vast majority of what we're doing is just algebra, right? So the calculus concept is this: what's the definition of the derivative, and then how we compute that. It's pretty much all based on algebra. And then that's not going to leave you. As you go on to Calc 2 and Calc 3, you'll learn certain concepts, but in order to compute those things, it relies heavily on algebra and trig. All right. So what's the derivative of the square root of x? So if you, again, if we're using the definition, you should always start out finding f of x plus h, because that has to be inserted into the definition. So f of x plus h is just the square root of x plus h. And then what we compute the limit as h approaches 0 on f of x plus h minus f of x all over h. So how do we simplify or compute this limit? What are we going to use? The conjugate. The conjugate of the numerator is what? Right, yep. Square root of x plus h plus the square root of x on top and bottom. Okay, so what is the, what's the numerator multiplied together?
X plus h.
Okay, good. X plus h. There we go. It's minus x. All over all of this denominator. Okay, so here again, simplifying the numerator, we've got an h up top and an h on the bottom. Those will go away. What's the numerator? Okay, it's 1.
Why do the H's go weird?
Because this is 0.
Oh.
That and that give us 0, and then so it's just h over h is 1. Yeah. All right, now as h goes to 0, what do we get? 1 over 2 of those, right? So you have 1 over 2 times root x. Or 1/2 times x to the negative 1/2. Just however you want to write that. So let me write these here. Any questions on that? I know that was fast, but hopefully we've seen enough of these to sort of remember how to do them. But are you all right with that? The and? Where's the and coming in at?
It's coming to where I wrote the equation wrong.
It's like when you're uncomfortable because you know that you can do it. It's just so intense.
Yeah.
You're not really jumping.
Yeah. Yeah.
It's like, can I do it? Yes, but do I want to? That's for the discomfort.
Well, I mean, at least you have the ability to do that, right? You gotta harness the ability by practicing. That's, I mean, you gotta look at it that way.
This is just the samurai teaching the apprentice. Oh, we're just getting whacked with sticks right now.
Figure it out.
Okay. So to change directions a little bit in 3-2, the derivative function, and then we'll talk about how we graph the derivative. So I know there's a lot of words here, but it's all relevant to how when we're given a function and it says, hey, here's the graph of f of x, what does the graph of its derivative look like? We're looking for these 4 things. Okay, the graph of the derivative, which is just the slopes of the tangent lines have the same inputs, and we should specify it's not always, this isn't always the same inputs, it really just depends on the function. And I'll put that here. For the most part, it's not like we're drastically shifting the x values or anything like that. But it's the outputs are the slopes at every single point. So I think it's really helpful, at least initially, when you're given the graph of a function and it says graph the derivative, to just literally put your pencil or your pen on the function and just look at your pencil and say, well, is the slope of that line positive or negative? And as I move my pencil across my function, I can start to measure the slope. Is it positive or negative? Okay. So where the slopes of the graph given f of x is positive, that indicates that your derivative will be above the x-axis, right? Because your outputs are positive numbers. They're positive slopes. Where the slope on the graph is negative, the output on your derivative graph will be below the x-axis for negative values. Where the slopes are horizontal, that's where you have a 0 on the derivative, because right, a horizontal line has a slope of 0. So those are going to give us our x-intercepts, if you will, on the graph of the derivative. And we have to look at where the slope of the function given is undefined. Okay. So the first three should be fairly intuitive when we're just thinking about, is this positive or negative, or is it flat? Where the derivative or the slope is undefined, we have to look at this. So when is a function not differentiable at a point? So a function f is not differentiable at an x value of a for any of these conditions. Okay. So we can't define a derivative at a point if the function's not continuous at a point. Okay. Figure 318 just gives us a brief example of that. Here's 318. We can't define the derivative here at a because the function's not continuous at a. The other instance is where the function has a corner. They're calling it a corner. So this corner here, the derivative or the slope of the tangent line isn't defined at a corner because as we come from both directions, the slopes of the lines are vastly different. So this figure hopefully maybe illustrates that a little better. So, we're measuring the slope, all of those lines, that's fine, they're all defined, but once we get to this point, is it this line or is it this line? Which one is it?
Neither.
Yeah, so it's really neither. There's actually not a derivative at the corner.
Does it matter how obtuse or acute it is?
No. If it's like a super flat absolute value graph, it's still undefined.
Okay, cool.
Yeah. So even at like a really, really flat absolute value graph would not be defined at the corner. Because if you're looking at this function here, remember the definition of the derivative, it says the limit as h approaches 0. That's just the step size you are from a location. It doesn't indicate a direction, right? It just says as I get closer and closer to this value. It's really meant to be a two-sided definition, limit definition. So as I get closer and closer to this corner, the slopes of the tangent lines at all of these points are still constant, whatever that is. But, at that point, it's this line. From that direction, from the other direction, it's this slope. So since those two things aren't the same, we can't define a derivative there. Does that make sense? The reason we can define a derivative at something like this, at this point, is because this line, as it approaches here, gets flat, but also from the other direction, as I approach here, these slopes are all getting flat. And those two lines are from both directions end up being flat. So that's the difference between a corner and a curve. The third one, excuse me, is where the function has a vertical tangent. And we did kind of allude to that in chapter 2 when we computed a limit. We got like h to the negative 2/3. That example, you might not remember it. But the idea is that something like figure 320A and B, as we get to a particular point, the tangent line is vertical. So just that's an infinite slope. In that instance, you would get the slope of the tangent line coming out to be infinity. So you would see that clearly that the limit doesn't exist or the derivative doesn't exist because it would be infinite.
So it's the only difference between 3.18 and 3.20 is that one is they both have that vertical line, but one is continuous and one is not.
They're actually both continuous because this function, let's exaggerate it a little more. That function here in A is looking like that. So it's this sort of gradual curve that just keeps getting steeper and steeper. The tangent lines here and here are totally fine. It's just as we get further and further down, it's eventually vertical there. The figure, whatever, 320B is more like a cube root graph. You see that cube root graph is, kind of like this, and then it gets flat here and then extends that way. So that's kind of the difference between the two. All right. So then with those four things, we're going to look at next time, given a function, how do we graph its derivative? Do y'all have any questions before we go? All right. See ya. Have a great weekend.